Structural analysis with an NMR has been pretty straightforward to do in liquids for decades now. In solids, it's been slower to develop, and it's only really been possible in the last 20 years. Here's one of the first structures that was characterized. It's a small tripeptide. It was characterized by Rob Griffin's group in MIT using dipolar coupling methods. So they were able to label the C13 and N15 sites and then get distance constraints throughout the molecule and put the structure together. Another molecule appeared about the same time. It was a smaller fungal product, and this was characterized at natural abundance. So it's been possible for about 20 years now to do structural analysis in solids with both labeled and unlabeled materials. In our group, we've done structural analysis in solids with something called the chemical shift tensor. It's given by three different shifts for every nucleus that show the shielding in the X, Y, and the Z direction. We typically don't know which is X, which is Y, and which is Z, so we just list them by magnitude as 1, 1, 2, 2, and 3, 3, with the 1, 1 being the largest and the 3, 3 being the smallest. The spectra that we typically use are shown here in the figure. So for each isotropic line for a given site for the carbon-13, we'll get this pattern in the second dimension called the powder pattern, and from that we can actually derive the three shifts using numerical fitting. This example I think is lauric acid, and it's given in this 2016 paper if you're interested in looking at it. The methodology that we use is proven to be pretty general. Here's some examples of structure we've solved over the last 20 years. Ambuic acid is this biofilm inhibitor that came out of a fungus in Papua New Guinea. Catechin is one of the best water-soluble antioxidants, and it occurs in all sorts of fruits and vegetables that you eat. And we published that one in 2010. Paclitaxel, the anti-cancer drug, that was published 13 years ago. So lots of structure have now been solved. In our group, we were able to solve them all at natural abundance. Other methods are now available that can allow for labeled materials too. And here's some other references if you have interest in looking at how to do structure with the chemical shift tensor analysis. One of the interesting questions that comes up if you're going to do structural analysis with a chemical shift is which is the best parameter to employ for structural studies? Well, we just said there's three values that you get, the 1, 1, 2, 2, and 3, 3 value. And we usually select by just making a series of model candidate structures, and then we see where we get agreement with experimental data. And I would contend that these principal values, the 1, 1, 2, 2, and 3, 3, are probably one of the best ways to do the analysis. The reason this actually even becomes an issue is because the IUPAC has recommended that we combine principal values in some mathematical combination to create new parameters. And the values that they recommend are the isotropic, asymmetry, and the anisotropy. Other values have also been proposed by several other people, but I kind of want to talk to you about why using any of these might be problematic and discuss which may be more advantageous than others. If you look at the current proposed recommendations for principal values, in the top row there is the IUPAC recommendations, and they say you should use something called the isotropic shift, the anisotropy, which is given by two different definitions by the IUPAC, or the asymmetry. Robin Harris, who's the chair of this committee from the IUPAC, gives the definitions there, the first row. You can look at those. Since this is recorded, you can pause and take a look at this if you need to. In the second row there, Joan Mason has also made some other recommendations in 1993. She suggests the isotropic again, but she has something in the middle column there which she calls the skew. It's defined a different way. And then another one in the third column called the span. And those are different ways of reporting these numbers. Michael Mehring and David Grant have also made recommendations for this. Mehring, in his 1976 book, talked about the isotropic. He also recommends the anisotropy, and then he suggests another thing called the asymmetry, but he defines it slightly differently. In his case, the asymmetry is 1, 1 minus 2, 2. David Grant has also made recommendations in a 2009 article. He suggests that you use the isotropic, something he calls the eccentricity in the middle column there, and then the span, which is something that he has in common with John Mason, which is 1, 1 minus 3, 3. Let's talk about these separately. If you look at just Michael Mehring and David Grant's recommendations, they have a nice property that they're linearly independent. So if you use this mathematical test from linear algebra you can do for linear independence, you can show that these all have this behavior of being linearly independent. And this is nice because it has the same behavior as the individual principal values. You should be able to select model structures in an independent manner because they're not weighted by one another, these different parameters. And I think they would be better than the IUPAC parameters for reasons I'll talk about on the next slide. If we use the individual principal values, just the 1, 1, 2, 2, and 3, 3, they should behave similarly. So I don't know if there's any advantage using this way over the principal values, but if you want to use linear combinations, these are two ways that have this nice behavior of linear independence. If you look at the IUPAC recommendations and those from John Mason, they are not independent. For example, if you look at this, the asymmetry contains both the anisotropy and the isotropic value. Likewise, the anisotropy contains the isotropic value. This means that if populations of candidate models were selected using these parameters, you're going to have some overlap. One of these values is weighted by another one. They're not independent of one another. And so you would expect that they wouldn't select as cleanly or as accurately as the individual principal values themselves. John Mason's proposed parameters have a similar problem because the skew contains the span. So if you want to do analysis of structure using shift tensor data, I think using the principal values or those parameters derived by Michael Mehring or David Grant may have some advantages. Thanks for listening.